My name is Timur Doumler. I work at JetBrains. I work on a C-line IDE, and I do the one of the people who developed the C++ front end of C-line. So today we're going to talk about class template argument deduction. We already had a talk about it yesterday. Was anyone in that talk? Yep. Okay. So it's going to be some of the similar material here. Right. So I think class template argument deduction is actually a really cool feature because it lets us write cleaner, shorter, more readable code, and that's always a good thing. Unfortunately, when you try to figure out how it works and kind of dig down into the details, then it tends to get a little bit complicated, and there are a few traps and kind of unexpected things. So today in this talk, I want to kind of talk about those to get to tell you a little bit more about how it works and what the traps and things that you have to keep in mind are. So we're going to talk about, first of all, how does it work, class template argument deduction? Oh, by the way, class template argument deduction is quite long, so I'm going to try to refer to it as CTAD. Right, so how does it work? Then how do we use CTAD in the STL? And then if you're a library maintainer, how do you use CTAD with your own library classes? Then pitfalls. We're going to talk about deduction guides. We're going to talk about some meta-programming techniques you can use to develop, write deduction guides. Going to talk about a few coding guidelines that you might want to keep in mind. And if you get to it, a few bonus slides about possible C++20 extensions to CTAD. Right, class template argument deduction. So this is not really something new because we already had template argument deduction in C++ since C++ 98. And this is basically just an extension of existing template argument deduction. So template argument deduction in C++ 98 works on functions, on freestanding functions, templates, function templates. For example, min. Min is a templated function. Obviously, if you use min, you don't have to specify the template arguments by hand. You can just give it 2 integers, and it's going to deduce the template arguments from the template arguments from the function arguments that you give it through some rules that are in C++ since 98. So if you give it 2 ints, it's going to deduce min int and instantiate that. If you're going to give it floats, it's going to instantiate that. If you give it a float and an int, it's going to say, well, conflicting types, I can't deduce this. I'm expecting one template to deduce one template argument. I get 2 different ones. I can't do this. So I presume that kind of you know how this works because we're not going to talk about function template argument deduction. We're going to talk about how CTAD builds on top of that. So what we want is we want to use it not just for functions, but also for classes. For example, pair. Unfortunately, in C++ 98, it doesn't work. If you want to instantiate a pair, you always have to specify the template arguments by hand. So if you have a pair of a string and an int, and you give it a string and an int, well, it actually already knows what you're doing, but you still have to write by hand the string and int, and that's kind of annoying. In C++ 11, it got a bit better. Because C++ 11 introduced auto as a keyword, so now it also introduced this workaround where we can use freestanding functions where template argument deduction works. So we introduced these make functions. For example, for pair, you have make pair, and then you give it a string and an int, and then it's going to deduce pair. In this case, you give it a string literal, so it's going to deduce const char star and int. So you don't have to write those template arguments. You can just store them in the object and say auto. But it's still not quite what you want because it's still an actual function call, right? So it's actually going to generate code, which might or might not be optimized away later. It's still also syntactically calling a freestanding functions, so you have to deal with forwarding arguments, decaying arguments. It's also a bit too verbose. This whole thing feels more like a workaround and not like a proper solution. But in C++ 14, it got nothing really changed. So if in this case, if you want to deduce a string, so the only modification here that we got these string-defined, user-defined literals, so you could do like, in this case, THS and then the little s, and then it's going to turn the const char star into a string, and then you're going to get a string. Unfortunately, you also have to use this namespace whenever you use these string literals. But what we really want to write is this, right? And the good news is in C++ 17 we can do just that. this works, and this is going to deduce, if you use the little s to say string, it's going to deduce you a pair and for string and an int. So that's nice code, and that now compiles and does what you expect. So that's kind of the good news. How does this work? So I can, of course, refer you to the relevant section, the standard overmatch class deduct, which describes the rules. But it's a little bit complicated, and there's also a few rules in there that you don't really have to know in detail if you're not an implementer. So I'm just going to go through it here in a little bit more simplified way. The most important thing about how CTAD works is that you always have two steps, two separate steps. The first step is the deduction itself, like this is the actual CTAD, where it deduces the template arguments of the class that you want to create an object of. And then the second step is actually initializing that object. And it's really important to keep in mind that those are two separate steps. So if you get that, you kind of get already how it works. Let's look at the first step. So let's say we have a templated class, something like a simple wrapper, like a pair, just for example purposes. So this is not standard pair. Standard pair looks a little bit more complicated. This is a very, very simplified version of it. So it's basically some class that has two members and has a constructor that takes, const tref or tref for both of these members and initializes them, and you want to be able to write that and have it deduce pair of string and int. How does it work? The first thing that happens is the compiler sees, okay, you want to initialize an object, you have written pair, which is a template name. So it's a template that has template arguments. So none of them have like default values or anything, so they're not known. And you haven't specified them, right? You have just written the template name. And then the compiler says, okay, here I need to do CTAD. So the second thing it does is, okay, I need to do CTAD. I need to look at the constructors, because you're obviously calling a constructor here. So first step is, it sees, okay, you have two constructors there. You probably want to call one of them. But you have class template arguments. Now what we're going to do is perform CTAD. How does it work? Take the constructors, take the template arguments of the class, and let's pretend for a minute that those constructors are actually functions. Not constructors, but actually like normal functions. And then let's pretend that they have the template arguments that the class has. So we're not using the constructors here, but we're generating on the fly these kind of not really existing functions from the constructors by taking the template arguments of the class, the template arguments of the constructors if they have any, putting them together and creating these kind of, I don't want to say virtual functions because that means something else, synthesized functions. And those are called deduction candidates. And with those functions, we're going to look again at the call down there, and then we're going to perform template argument deduction just the same way we always did for functions in C++98. And we're also going to perform overload resolution the same way we always do for function. And then we're hopefully going to get a match, right? So this call matches the signature of this function. So we have two template arguments which you're going to deduce from the two arguments that you've given the function. So this is going to deduce string and int for t and u. And we're going to inject this back into the call and say, okay, now we know what class it is. So this is all just used to determine what class you're actually trying to instantiate. So we found a match. We found a deduction candidate. We're going to take the template arguments that were deduced from this candidate. We're going to apply them to the class, to the template that we're trying to use here. So, excuse me. So now we know it's a pair of string and an int. CTAD succeeded. That's it. Step 1 is done. Now step 2 kicks in. We're actually going to instantiate it. So now we know it's a pair of string and int that takes a string and an int. We have two constructors, and now we know what the argument is. So we can instantiate this template, and we can call the right constructor, and we can actually construct our pair. So if you do it like this with R values, we're going to call the second constructor. If you do it with L values, we're going to call the first constructor. But it's going to be the same thing. Yeah, it's going to always deduce the same type. One thing that's important that people have asked me first time I gave this talk is, well, we have R value references here, but we kind of, during CTAD, pretend that this is a templated function. So do they not turn into forwarding references, and does everything not explode? And no, they don't. These are not forwarding references. There is a special rule in the standard that says forwarding references, this is only if the template arguments are actual templates of the actual function. So if they're template arguments coming from the class during this CTAD synthesization step, then this doesn't count. Like the forwarding reference rule does not kick in. All right. So this is how CTAD works, like the mechanics of it in the language. Does anyone have any questions about that at this point? Because it's really important that we are kind of on the same page on how this all works. Everyone understands? Cool, awesome. So this means we don't really need these make pair, make tuple, etc. functions anymore. There are some edge cases where they still do different things. Like, for example, make pair, if you give it a reference wrapper, it would unwrap it, whereas CTAD would not. I'm not exactly sure when you would need to make that, like what the exact use cases for that are. But there are a few subtle differences, but for most purposes, you don't need the make functions anymore. You would use CTAD instead. It doesn't work just for pair, it also works for tuple. So if you have a tuple, you can just write the tuple. You don't have to specify any template arguments. It's going to deduce them for you. One difference between CTAD and the make functions is that CTAD is all or nothing, which means that you have to specify all template arguments, and then you're going to get the old behavior, or you have to specify no template arguments at all, and then you're going to get CTAD. With functions, so you can't do this. So if you have a tuple, you want to specify the first argument as a string, so it's going to turn the const char star into a string, but then not specify the others. You can't do that with CTAD. That's an error. You have to always specify all arguments that don't have default values or no arguments. Whereas with the make function, you can do that. So with make tuple, you can say, well, std string is the first one, and then deduce the rest. So this is the difference between the make functions and CTAD. Right. I might say later something more about this during the bonus slides. But all right, let's keep going. Vector. CTAD works nicely with vector and all the other containers. So now you can just give vector an initializer list, and it's going to deduce the type of the vector from that initializer list. Also, if you give it conflicting types in there, it's going to give you an error. So that's really cool. There's one particular trap with vector, which is not really a new trap. It's an old trap. So in C++14, we have the situation where if you instantiate a vector int v with one int in curly braces, it's going to say that's an initializer list. It's going to create a vector with one integer in there that is 3. If you do the same with parens, it's going to call another constructor, and it's going to have like 3 default constructed ints in there, so 3 zeros. So these two are going to do different things. And with CTAD, they also do different things, except that if you don't specify the template argument, the first one is going to deduce it because it's an initializer list. The second one will say, well, you're calling this constructor like 3 default constructed values of type t, but what's type t? I don't know that. So then deduction will just fail. So here you need to remember to use the curly braces. Vector also has another really nice constructor that works with CTAD, so you can give it a pair of 2 iterators. So they don't have to be vector iterators, they can actually be any kind of iterator. And then this is going to deduce vector int for you as well, right? So because in this case, range is a range of integers. It's also a vector. How does that work? Right. So this obviously doesn't work out of the box because you give it iterators and it's deducing vector of int for you. So this is some kind of magic going on. So this is again not actually std vector, it's a simplified version. It has this constructor which takes 2 iterators, and it has a template argument, template type name iterator. And then also the vector itself has a template argument. Now, if you call it like this with 2 iterators, and then you do CTAD in the first phase, as we already learned, you synthesize this function where you take the class template argument and you put it in front of the function, right? So now you're going to end up with this kind of function. And then you try to call it, and then the compiler will say, well, okay, so I can deduce iter, right? Because these are the 2 iterators that you gave me, but I can't deduce t. There's no argument, there's no argument t or anything resembling t. So how do I deduce t? It turns out it's another feature. You can help the compiler to do these things by writing an explicit deduction guide. So in these cases where the compiler can't automatically deduce the type, you can write this new syntax where you have in the front something that looks like a constructor, essentially, like a constructor signature, and then you have an arrow, and then you have an instantiation of the template, right? So this is going to tell you, okay, if you have a constructor that takes 2 iterators, then deduce the vector by basically unwrapping the iterator and figuring out what the value type of that iterator is, and use that for t to actually have a vector of t. So this is the syntax. It looks a little bit like a function with a trailing return type, but no auto in front, but it's a completely different beast. It's not a function, it's not a class, it's not a template instantiation, it's like a new kind of entity. Yeah, and with that, basically what happens is that this function signature before the arrow, it's going to be added to the overload set during step 1. When we synthesize these functions, and if we add the deduction guide in there, and then if the deduction guide matches during overload resolution, we're going to use that. And then we're going to deduce whatever is after the arrow. And that's going to be our type. Okay. Everyone okay with that? Cool. Of course, if you give it, for example, 2 ints, you get an error. Because there are no iterator traits int. In this case, the deduction fails. Well, actually not, because there are other constructors in vector, but not on this slide. So we're going to see later how this works. There's another trap here, actually a few of them. Things depend on the order. So if you have this deduction guide and you use it after that, it works. But if you flip it around, then it's going to fail. So if you write the deduction guide after you use it, it's not going to consider the deduction guide. So the order matters. A recommendation would be if you write deduction guides for your own class to put them immediately after the class declaration, because they're really part of your class's interface in a way. So and if you put them immediately after the kind of closing brace semicolon, then there's no danger of anyone using them before you define them. Of course, there's other cases where you use a library where someone didn't define deduction guides, and you want to have deduction guides. You can basically open the namespace of that library, write your own deduction guide for that other library, and then use that. You can do that, but then of course the library maintainer might add deduction guides later, and they might conflict with the ones that you wrote. So you really need to be careful with that. Actually, this leads us to another rule. Deduction guides always have to be in the same scope of the class that they refer to, right? So if vector is in namespace std, then deduction guide also has to be in namespace std. So you can't add additional deduction guides for vector because you can't add anything to namespace std. Well, with a few exceptions, but this is not one of them. Next trap, list initialization has priority. So if you do this kind of thing, you have a range and you have doesn't matter, you have 2 iterators, and you initialize a vector with a pair of iterators, it's going to deduce vector int if you use round parens, right? However, if you use curlies, it's going to be an initializer list, and vector has a constructor that takes a still initializer list. And the rule during overload resolution here is that this is going to have priority. So in this case, you're not going to call the constructor with the 2 iterators and use the deduction guide, but instead you're going to call the initializer list constructor, you're going to construct a vector of 2 iterators. Right? So you need to be careful because you're not writing what kind of vector you're instantiating. So you need to be careful when you use parens or curlies. So the same thing works for, obviously, other sequence containers like list, deck, etc. There's also the same trap here with range containers range constructors that you need to be careful to use parens instead of curlies. The range thing doesn't work with array because array has the size of array as compile time, and so that doesn't work. Doesn't have that constructor. Set. Yeah, why would it work with set? It does work with set. It works actually really nicely with set. You can give it a range, like initializer list. It's going to deduce the correct set. You can give it, again, one pair of iterators. It's going to deduce the correct set as long as you don't use braces. Set is actually really cool because set has even more constructors. So set has one constructor that takes an initializer list and a comparator, right? Now, the comparator is an additional template argument of set. But that can be deduced as well. So you can give it an initializer list and a lambda that is your comparison operation. It's going to deduce the type of the comparator from the lambda that you gave it. So you can use your custom comparator and you still don't have to specify any template arguments. That's really, really cool. And there's even another constructor that takes a pair of iterators and then a comparator, and this also works. So this really makes you look again into all the nice constructors that all the STL containers have and all the cool stuff that you can do with it. Map. Well, map, unfortunately, is a little bit more complicated. You would like this to work, right? So this is what you would expect you would expect this to deduce map of string and int, right? Unfortunately, that's not going to work. You're going to get an error if you try to do that. The reason is, whenever you have these nested init lists, CTAD doesn't really work. So what you would have to do is you would have to either again specify the template arguments as you did before C++17, or if you know that the elements of map are pairs, you can add these pairs here, and so you don't have to at least specify the element type. This is not really ideal, but it's not really. It wouldn't really work because if you have these nested braced init lists, then they are not actually they're not like std initializer list objects, right? So they are kind of this kind of special braced list kind of entity, and you can't use that. It's not a type, right? So like a list and braces is in itself not a type. So you can't deduce anything from that. If it's just the only thing you have, it's going to match the initializer list constructor, so you can use that. But if it's nested inside another list, then it doesn't really work. CTAD does work, though, with copy constructors. So if you have one vector, yes?
Do you have to specify for every of the argument in the bottom example, or just the first one?
In the bottom example, the question was whether you have to repeat pair. Yes, you do. Because if you specify the first pair, and then you have the second one, and you just have a braced init list, you still have this kind of thing that doesn't have a type. CTAD with copy constructors. You can have a vector, and you can have another vector, and you give it the first vector, and you copy it, and then the copy constructor will also deduce that the first vector is a vector of int, and so the second vector is also going to be a vector of int. And that works, obviously, with all these classes as well, vector, pair, tuple, etc. There is, however, one really nasty trap here. So this copy, there is this rule where if you, so there's this copy deduction candidate, which is essentially like the copy constructor, but during the CTAD phase. And the rule is that this has a precedence over, for example, the initializer list constructor during overload resolution. So what's going to happen is if you have a tuple and you give it another tuple in braces, it's going to call the copy constructor because that has precedence. If you give it two tuples, however, like here, it's going to construct a tuple of tuples, right? So all of a sudden, depending on whether you have one argument or more than one argument, you have a very, very different kind of deduction going on here. So this is a nasty problem, and it hits you even harder if you write generic code. And for example, you have a variadic template, right? You have like a parameter pack where you don't know if it's no arguments, one argument, or multiple arguments, and then you create, for example, a tuple in there using CTAD and kind of forwarding this parameter pack. And then depending on whether it's empty, there's one element, and there's more than one element, there's like 3 completely different things are going to happen. And this can be dangerous. So it's worth keeping in mind that with these classes, if you give them one element in braces, they typically will copy. And if you give them more than one element in braces, they're going to use the list initialization. Some more classes where CTAD is really, really cool and useful. For example, one class where frequently it's really annoying to write out the template argument are lock guards. Right, so you have to write that all the time. In C++17, you don't have to do that anymore. You can just omit the template argument. It's going to deduce it from the mutex that you give it. Actually, in C++17, you don't even write lockguard anymore. You write scoped lock, because that's the same as lockguard, but better because it's variadic. It can lock several mutexes at once. So lockguard is not recommended anymore. You should use scoped lock instead. I expect that we're going to deprecate lockguard eventually. CTAD also works if you have no constructor arguments at all, like here. For example, you have these like less, greater, and these little helpers in the STL, which you would like default construct and then pass into an algorithm. And they have one template argument, which is defaulted to void, which is kind of the default less operator. But then you also always still had to write these empty angry brackets. Now with CTAD, you don't have to do that anymore. So you can just construct it as if it were not a template at all, and it's gonna. So the constructor doesn't actually take any arguments at all, but you still have the template argument from the template, and that has a default value, so that's just going to be used. So you can omit these angry brackets. CTAD works with all these like little like wrapper or bigger and useful wrapper classes that wrap a type. It works with optional, it works with atomic, it works with complex. There's one little trap with complex where if you, for example, do something like this, where you construct a complex from 2 ints, that's going to deduce your complex int. That's probably not what you wanted. You probably wanted float or double. Complex int may or may not be even there. If it's there, it's probably not what you wanted. So you need to be careful that the arguments that you give actually match the template argument that you want to deduce. And this is one of the examples where, if you're actually the maintainer of a library, you should really be careful because CTAD silently expands the interface of a templated class, right? So you have a library which uses, template classes like, for example, StatComplex, and people have been happily using it for many years. And now all of a sudden they switch to a C++17 compiler, they get CTAD. You didn't change anything in your library at all. Your users get CTAD, all of a sudden they can omit the template arguments. And sometimes, like with the StatComplex there, what happens is may or may not be what you actually intended. So sometimes it may make it easier to use your class template interfaces incorrectly. So if you have a library and you have templated classes, then it's worth kind of going back into your code base and look at the constructors that you have and kind of the interface that you have there and see whether any of this could be a problem with CTAD. Because a good user interface is, of course, an interface that's easy to use correctly and hard to use incorrectly. And most of the time, CTAD does what you expect and is really nice, but sometimes there are these cases where it actually creates new problems. And complex, maybe, you can argue, complex int, that's fine. It's probably a use case for it. But there's much worse cases of this, like with smart pointers, for example. Let's say you have a struct, some class, it doesn't even matter what it is. It's some class that has some constructor that takes some arguments. And you want to construct a shared pointer for it. And you would expect this to work, right? You say shared pointer, you omit the template argument. You give it a pointer of some type, and you would expect that it would deduce shared pointer of citizen in this case for you, right? That doesn't work. And it's good that it doesn't work. So on purpose in the STL, shared pointer does not work with CTAD if you give it a pointer. This is a case where if you would just magically enable CTAD and this kind of stuff would work, it would be very dangerous. So with make shared, you still have to use with shared pointer, you still have to use make shared and CFS 17, and the same with unique pointer. And why is that? Because sometimes these make functions actually are better. For example, for shared pointer, make shared is actually more efficient because it's one allocation instead of two if you like directly construct it. It has also exception safety built in, right? So if the constructor of the thing that you're trying to put into the pointer throws, then make shared is going to make sure that it's not going to cause a memory leak if it throws in the middle of that process. And then the third reason why CTAD would be dangerous here is really nasty, and it has to do with arrays. So what would happen if that would compile, right? So you have a unique pointer, and you give it an array. And there's valid use cases for unique pointers of arrays, right? Like unique pointers to arrays. Sometimes you can use them instead of like a vector, and there's good use cases for them. But in this case, this is not what you would get, right? So function arguments decay. So if you give it an array, it's going to decay into a pointer. And if that would work with CTAD, it would deduce you unique pointer of int and not of int array. And then if that would go out of scope, it would call delete not the array version, but the normal version. And then undefined behavior, everything explodes, right? Bad. Or at least you would get a memory leak. So that doesn't compile, and you, in this case, if you want a unique pointer of arrays, you have to specify it. So again, if you have a library class, when do you not want your users to use CTAD? When do you want to disable CTAD and make sure CTAD doesn't work? If CTAD, like we just saw with the smart pointers, if it would lead to wrong or dangerous code, if it would not instantiate what you want, like the pointer version instead of the array version, for example, if it would lead to code that's less efficient, like with make shared, which actually saves you an allocation if you use it, if it would not provide the functionality you want, for example, exception safety, then you would not want to use it. You would want to use your make functions. And sometimes CTAD just wouldn't work because of the way your class is written. Sometimes it would work out of the box, and you need to make sure that it doesn't. So how do we disable CTAD? Let's say you have your own smart pointer class. There are some libraries that have these kind of classes. So it takes a pointer. So this is kind of a naive smart pointer, right? In some library. It takes a pointer. It kind of initializes itself with that pointer, and then it would manage that pointer and maybe call delete on a destructor or whatever. And then if you just leave this, so this is, for example, you have a class that you had already since like many years, and now you get CTAD, and now all of a sudden your users can instantiate it like this, and then you would kind of get the pointer version instead of the array version because the array decays. So you don't want that. You want to make sure that this is not going to compile. Like as it is on the slide, it would compile, it would be bad. How do you make sure it does not compile? There are several techniques for it. One technique is, I don't think it has an official name, but I call it the type identity idiom. So you can use this little type wrapper. So you're going to get this in C++20. It was actually surprisingly hard to get this really small, simple thing into the standard. So if you're interested in like kind of the backstory, you can read the paper. Anyway, that doesn't matter. So what you do is you create this tiny little wrapper which doesn't really do anything. It's a template, and it just has a template argument, and it provides a member type def, which is just that same type, right? So it's a really stupid wrapper. It just says, okay, give me a type T, and I have an alias inside, which is just the same type, right? It's completely useless. But what you can do with it is instead of, let me go back to the original code. So the original code was taking a T star as an argument. So here instead, you can say, well, let's take type identity T star instead of T star. And that's exactly the same type, right? You didn't change anything. But the trick is, now in order to find out that it's the same type, you have to go to this type identity template. So you have to like instantiate this other template in order to find out that it's the same type. And CTAD is not going to do that. This is what we call a non-deduced context. Like during CTAD, it's a non-deduced context. You're not going to deduce like you're not going to look into other templates and try to instantiate them and look into them in order to deduce some type. So if CTAD goes ahead and then sees another template in there, or a type depending on the template, it's going to say, well, I'm not going to deduce that, stop. CTAD fails. And this is exactly what you want here, right? So this way you disable CTAD on this constructor. And this type identity idiom is really, really cool because it also works on freestanding functions. So you can also use it to disable regular template argument deduction on just regular functions. You can also use it selectively just on some of the parameters. That's not the only technique. Another technique, what you can do is, instead of using this argument, you can have a member type def. So instead of using t star as the argument for the constructor, you can have a type def. CTAD looks through these type defs. So if you just do it like this, instead of t star, you say using pointer equals t star and then use pointer as the argument type. Because the type def is inside your class that you're deducing, it's still going to see that. It's kind of like sees through all the type defs inside the class you're in. But then again, you can add something like that up there. So add pointer t is a bit similar to the type identity that I used before. It's the same type, right? Add pointer t is just t star. But in order to find out, you need to instantiate add pointer t, like the template. It's another template. You're not going to do that. So again, it's a non-deduced context. CTAD will fail. The third technique is to actually have your constructor itself templated with another template argument. And then what's going to happen is, during deduction, it will say, well, you're giving it a u, and the constructor has a template argument u, so I can deduce that, but I can't deduce t, right? I don't know that u and t are related. And the fact that t is constructed from u later inside, that's like CTAD is not going to know anything about that. It's not going to look inside there. So again, CTAD will fail. So these are kind of ways how you can make sure that CTAD actually doesn't do what it normally does. Anyone has questions about this section? No? Cool. Let's have some more fun with deduction guides. So the STL has some really, really cool deduction guides, and if you look into them, if you look in there, then it also gives you hints about how to write your own. For example, function has a really cool one, actually two. So you can construct a std function from a function pointer or from an object that has a call operator or a lambda, but basically anything callable. So for raw function pointers, it works here, and it has this deduction guide where basically it takes the type of the function pointer and kind of unwraps takes away the pointer, kind of unwraps it, takes the return type and the arguments and uses them as the template argument for the std function. And then it also has deduction guides for the kind of functor object case, like F2 and F3 here, which are a bit more complicated and magic, but they also work. Another important thing about deduction guides is that they sphinad. That's really, really important. So coming back to the vector here, so we had this kind of naive vector where we had this constructor that takes two iterators. Of course, we have other constructors in vector that also take two arguments. For example, we have one that takes a count and a value. Now, we have this deduction guide down there which says, okay, if you have two arguments that are kind of the same, then, if they're like unwrap, like let's say it's an iterator type, then unwrap the value type of the iterator type and use the value type. Now, if you call it with two integers, then obviously that deduction guide is not going to match, right? But you're not going to get an error. So the deduction guide is going to say, well, it matches the signature of the deduction guide, but then after the arrow, this thing, it creates an error because int doesn't have iterator. There's no iterator traits of int, and int doesn't have a value type. It doesn't work. But then it's not going to create an error. It's just going to sphinay away. It's going to just be removed from the overload set, and then overload resolution keeps going and finds the other constructor, which takes a count and a value, and that's the thing that you actually want to call. So it's going to successfully deduce vector int using that second constructor. It's all going to work. It's all going to be wonderful. You had a question?
Yes. How comes in the deduction guides you don't have to say vector, colon, colon, vector?
The question was, why don't you have to say vector, colon, colon, vector in the deduction guide?
Outside of extract, right?
Yes, but it's a special syntax. So deduction guides have this grammar where, so the first thing needs to be like a constructor signature that starts with maybe some template, some templates, and then vector, like the name of the. So it looks like a constructor signature as if it were inside the class. So you don't put vector, colon, colon, vector. But also it has to be in the same scope as vector to work, right? So you can't put it in another scope. So you can never get into the situation where, no, you would have to deal with scopes here.
That doesn't have to be outside of the struct itself?
It has to be outside of the struct itself, but in the same scope as the class itself. So it has to be namespace std.
So I cannot just like merge it inside the vector constructor, right?
No, it's not a constructor. It's a different thing. So the first part of it looks like the declaration of a constructor, and then instead of the semicolon you have the arrow, and then you have an instantiation of the same template. A specialization of the same template. That's just the syntax.
Will this work with concepts the way I expected?
Question is, would that work with concepts? Let's take this question offline. It's not an easy question. I have not looked into how CTAD and concepts interact. I've read a few emails on the committee mailing list where like people were talking about this, but I have not really deeply looked into it. But there are some interactions between them, but I don't know about them yet, but I haven't really looked into it. But maybe we can take this offline and discuss it. There are some people here at the conference who have looked into this a bit deeper, how this interacts with contracts. Concepts, you said. Yeah. Okay, so deduction guides work really well with Sphene. And you can actually use that. This is like a technique, right? So let's say you have a deduction guide like this one, where, okay, if it's an iterator, you want to, use the value type of the iterator for the template argument. But let's say, like, actually vector does something like that. It only works with input iterators, right? You can't construct a vector from an output iterator. So what you can do is you can write it like this. It looks horrible, but it's actually okay. So you write a meta function which says, okay, this is the kind of usual Sphene technique with enable if, right? So if a thing inside is it's something valid, then this is going to be a type, and if it's not valid, it's going to not be a valid type, and then it's going to be Sphene'd away. In this case, what you write here is, okay, enable this type if the iterator that we're deducing is an input iterator. That's exactly what we're saying here. And if it's not an input iterator, then enable if t will not generate a valid type, and the whole thing is going to Sphene away. So this kind of Sphene on deduction guides is a really powerful technique. Another great example of how you can use Sphene with deduction guides is with std array. Std array has a great deduction guide. So std array is essentially something like, again, a bit simplified, but something like this. It has template type name t, and then the size of the array is the other non-type template parameter, and then it has the data inside somehow. And then it works with CTAD, right? This works and deduces array int 5. Obviously, that's not going to work without the deduction guide because we have this n template parameter in there, and that's not going to be deduced with the usual CTAD rule phase 1 thing, right? So we need to help it with the deduction guide. The deduction guide can look something like this, and that's the first version of it. All right, so constructor signature, right? We have a constructor that takes, some number of arguments, and then we're gonna basically deduce the type of the array from the first argument, and then we're gonna deduce the size of the array from this size of the, like basically how many arguments we have in total. And this works. There were questions about that? So this obviously matches that, and then the 2 is going to give you the int, and then the size of the parameter pack is going to give you the 5. and then you instantiate an array of int 5, right? Question?
Does there have to be a constructor which has matching signature, or?
Well, yeah. So the thing before the arrow needs to be a signature of a constructor, and it needs to match the instantiation that you wrote. That's how it works.
So there is a constructor with exactly the same signature?
No, there is no construct. The question was whether there's a constructor in array with the same signature. No, there is not. Deduction guides are separate from constructors. You have constructors, and they're used. So we synthesize deduction candidates from the constructors, as we saw in the beginning of the talk. And then we also take the guides as well, and we add them to this whole set. And then we perform overload resolution on the whole set. So you don't need a constructor in order to use the deduction guide. We're gonna see more examples if there's time about this later. So actually, this deduction guide is not correct yet, because the way I've written it here, this would also work. So if you have a float and an int, you have like different types. It's going to deduce float t for float for t from the first argument, and it's going to convert the second int to float, and not like that's not what you want, right? You want that to fail, because you want that to behave the same way as normal list initialization behaves. So how can we make this fail? Well, we need to write another condition, like a Swine kind of thing, where we say, and also all of these arguments have to be of the same type, right? So we just write that inside an enable if, right? So there's this meta function which returns true if all of its template arguments are the same type, right? And then because you have a parameter pack, you have a fold expression where you kind of say all of them should be the same, and then you enable the type if that's the case. And this is actually how the array deduction guide actually looks like. So this would be a standard conforming deduction guide for array. There's some more traps, not with this, with other aspects. We have 12 minutes left. Let me speed up a little bit. So one important thing about CTAD is this whole procedure only considers the primary template. So you can have a primary template and specializations, right? And CTAD is never going to look into the specializations for phase one. So for example, here you have a template type name, primary template foo, right? It doesn't even have to have a definition. Like CTAD can even work if it's just a declaration. And then you have a specialization of foo for int. And that has a constructor that takes an int. But the primary template doesn't have it. Now, if you try to instantiate foo from int, CTAD is not going to see the constructor takes an int because it's in a specialization. It's only going to look at the primary template. It doesn't have that constructor, so it doesn't find anything in this overload set, and it fails. But what you have to keep in mind, so CTAD phase one is using the primary template, but that's not necessarily what it's going to use in phase two, where you actually create the object. So here's like a funny example where, again, simple, similar. You have a primary template, but this time it has a constructor that takes a t, and then you have a specialization int that takes a const double ref, and then you instantiate the thing with an int. What does that do? Anyone wants to guess or knows? Convert to double. Convert what to double? Yes. Exactly. So what's going to happen is CTAD is going to look into the primary template, because that's what it does. It's going to find foo t, that the constructor. It's going to deduce t is an int, right? Phase one is done. And now you actually create the object. And then during this phase, which is independent, you're going to see, well, we have foo int, that's the type we deduced. There's a specialization foo int. So we're going to create a foo int. Foo int has a constructor that takes a double. So the int is going to get converted into the double. So that's a trap that you can fall into if you have constructor signatures that don't match the primary template. So recommendation would be don't do that. There might be use cases where you might want to have something like that, but I'm not aware of any. So if anyone knows use cases where this would be a bad recommendation, please tell me. I don't know if such, yeah?
To some extent, the specialization will ultimately be instantiated.
Sorry, what?
So in this case, the specialization for int would be instantiated.
Yes.
To the base template.
Yes. The first phase is not going to instantiate anything. It's just going to deduce the type. It's going to deduce foo int from the primary template. And then you actually, in phase 2, you create the object. And then that's where you actually instantiate foo int. Yes. So you instantiate the specialization. There's more nasty examples of stuff you can do with this. And don't have time to go into that. But this is kind of the basic thing where, CTAD uses the primary template, but actually then you get the specialization. Right. You can use CTAD not just in declarations, you can also use it in new expressions, you can use it in function style casts, where you kind of have this constructor call syntax. You don't get CTAD if you create pointers or references. So if you have stip pair ref and you do something, then you don't get it. Oh, with stip pair star, you always have to specify it.
Why?
Why? I don't know the exact reason why the committee chose not to allow it, but there probably is one. I can follow up on that. Let me skip that part. So yeah, so smart pointers don't have these constructors. So the constructors that take a pointer, a row pointer, they don't have CTAD, but you have these other constructors where a unique pointer takes another unique pointer, or a shared pointer takes a unique pointer. You can construct a shared pointer from a weak pointer from a shared pointer, etc. So those constructors, they all have CTAD. And here's another thing that is really important. So these deduction guides are for deduction only. And the signature, that's a little bit what you asked earlier. The signature doesn't have to match any kind of constructor. So let's take, for example, this shared pointer, and you can construct a shared pointer by moving a unique pointer into it. And the deduction guide for this looks like that, right? So it's a signature where shared pointer takes a unique pointer, and then you deduce shared pointer of t. Now you would say, well, this looks wrong, right? You wouldn't write a constructor like that where you would take the unique pointer by value. The extra constructor looks different, right? The extra constructor takes a unique pointer ref. The deduction guide doesn't. But that's okay, because it's still going to match during overload resolution, but it's not going to actually try to ever call the deduction guide as if it were a function. It's never going to try to actually move a unique pointer or copy a unique pointer into this kind of deduction guide thing. It's only used for deduction, so it doesn't have to match. Actually, it's a common technique where you have, if you're a constructor that takes a ref and another constructor takes a const ref, then you don't write two deduction guides that take const ref or ref, but you write one deduction guide which takes it by value, and this is going to match both cases, and then there's less for you to type. Yeah, guides actually don't have to be templates. So let's say you have a class, templated class, and it has a member of some string type inside, and you want that string type to be a template. And then for some reason, if you construct it with a const char like a C string literal, you don't want this to be a widget of string literal. You want it to be, so normally it would be deduced like this, but you want it to be a string view, right? Because string views are cool. So what you can do is you can just write a deduction guide that says, okay, well, if you find a const char, then instead deduce widget string view for me. Yeah. I wouldn't actually do that because it wouldn't be obvious from the call side, right? So if you have a constructor that you give it a string literal, and then what you get is a string view, that might be good, but it's not obvious from the place where you call it. So I would kind of use deduction guides in cases where you want to be able to omit the template arguments, but it should still be obvious what they would be, like with pair, with vector, all these examples. But you don't want to use deduction guides to say, well, you gave me this type, I'm going to use this other weird template specialization, and it's not going to be obvious for the user at all. So it's a bit, you can write really weird code with this that's really not obvious what it does, and basically the recommendation would be don't do that, because This is actually what we all want, right? We want code that is easy to read, easy to understand. Kind of this is the whole goal of this whole thing. And CTAD is a feature that lets you achieve that, or get better at that. And this should be kind of the goal of using it. Right, so I have 4 minutes left. So either I can take questions or I can show you some bonus slides about new cool stuff that might or might not be in C++20 and then ask questions offline later. What do you prefer? Bonus slides, cool, bonus slides. Right, so there are some proposals for C++20 in flight to change some of the CTAD rules, extend them, add some new features. So one of them is this one, which the main author is Mike Spertus, who's also the person who kind of is mainly responsible for CTAD in the first place. I'm a co-author on that paper. We are trying to basically fill some holes in the existing rules that I just described. It's a paper with like 4 things that we want to add, and we plan to submit it for San Diego for the next committee meeting. But this is it has not been approved by anyone, so this is still up for discussion. So there's like no guarantee whatsoever that this stuff is going to be in C++20. It's work in progress. So it's basically four things that we want to improve. Number 1, really annoying at the moment, aggregates always need explicit guides. So if you have an aggregate type, like very simple, this kind of thing that just wraps like two members. So you instantiate it, you get aggregate initialization with these curlies, which is really nice. But you have to specify the template argument. If you omit that, it doesn't work. Why does it not work? Because phase 1 during CTAD looks for constructors. An aggregate doesn't have a constructor. The whole aggregate initialization thing with curlies, that's not a constructor. So this is not going to be added to the overload set. So CTAD is going to say, well, no matching constructor, I can't deduce anything. And this is really annoying because those aggregates, they're really simple. It's really obvious what kind of deduction we want to use there, but still you would need to write this kind of more or less obvious deduction guide by hand. So basically that's the rule. Any aggregate needs a deduction guide if you wanted to work with CTAD. And then it would work, right? So then the curlies would match that guide signature, and then it would deduce name of T, and then it would perform aggregate initialization on name T, in this case name string. It wouldn't work with parens. So the first phase would succeed. It would deduce name string because it would match the guide. The second phase would say, well, but it's an aggregate, there's no constructor, so you're not using curlies, that's not aggregate initialization, so that's not going to work. So basically, our paper will propose to, first of all, synthesize this guide automatically, so you get CTAD for aggregates. And there's another paper by Ville, which says, maybe we also want to allow aggregate initialization with parens. So those 2 papers, they might kind of together create a situation where all of this might become valid code in C++20, but there's still some technical issues that we have to solve before we can kind of figure out how this would work exactly. Number 2, CTAD doesn't work with type aliases. It's really annoying. Like, for example, you have this, the example here is like you have this vector, PMR vector, which is like the template alias for a vector with a polymorphic allocator. So you obviously want to be able to omit this thing and write it like that. You can't because it's an alias. We will propose to allow CTAD on aliases. There's still some issues here which are unsolved yet. So it's, again, not yet exactly obvious how to do this. Number 3, you don't get CTAD from inherited constructors. So a lot of the time it's a good idea to kind of just inherit the constructors from the base class. But unfortunately, they don't participate in CTAD either at the moment. So what we would like to do is let CTAD also see into inherited constructors and also inherit explicit deduction guides. And the last thing is, as we already saw in CTAD, CTAD only works if you don't write any template arguments. So you can't like partially specialize them. That only works with the make functions. So we might allow this sometimes. It looks a little bit odd if you have like a tuple and you say string, and that's kind of the first one, you omit the rest, but then it's a tuple of like 4 elements. I'm not sure yet whether we should allow this, but there's other cases, like for example a set where you have a custom comparator and you want to specify the value type, but you don't want to you want the comparator type to be deduced, and that currently doesn't work. So it might be reasonable to allow this, but I'm not sure yet. Anyway, that's all I have. Thank you.